Okay, so we left off on vertically stretching and compressing the graph of sine. So if we fill in the table, the first row here we have all of the values for sine, and then the next row is when we multiply the parent function y equals sine x by 2. So we're multiplying all of the y values from sine by 2. And then the third row is 1/2 sine of x, where we're multiplying all the y values of the parent function by 1/2. And then we have the approximation of root 2, the decimal approximation of root 2 over 4 to help us with graphing. So I want to graph all three of these functions on the same xy plane so that we can really see what multiplying by those constants is doing to the graph of the parent function. So remember, for sine we start at 0, 0, and then we come up to or we have pi over 2 comma 1. Okay, put pi over 4 root 2 over 2. Oops. So make sure you're doing the best you can to make your graphs look curvy. Those points are a little too high up. Make sure you're doing the best you can to make sure your graph looks like a curve and there's no sharp corners. Yeah, those are points are maybe a little low. Okay, so we have one period of sine, and then remember we can extend the graph in both directions if needed. Okay, so there's the parent function sine, which we've already graphed, and then for the graph of y equals 2 times sine of x, start at 0, 0, and then we have pi over 4 root 2, which is approximately 1.41, and then pi over 2, 2. So you can graph one full period. And then extend the graph as needed. Oops. Oops, I messed that up. There we go. Okay, so then we have y equals 2 times sine of x, and last 1/2 times sine of x. Okay, so after graphing, okay, and then we have label it y equals to 1/2 sine of x. So we can see that when we multiply the parent function sine by positive 2, it doesn't do anything to the period of sine, but it does vertically stretch the graph of sine, making the waves much higher, okay, or the waves much longer. And then when we multiply sine by 1/2, which is the same as dividing sine by 2, we're vertically compressing the graph, so we're shortening those waves. And we'll skip this one. We skipped this one in class. It's just stretching cosine by a factor of 2 and compressing cosine by a factor of 2. So in general, the constant that sine or cosine is being multiplied by is going to stretch or compress the graph. So if the absolute value of a is greater than 1, then it's going to vertically stretch the graph. And then if absolute value of a is less than 1, it's going to vertically compress the graph. And if a is a negative value, remember that that's taking into account a vertical reflection or a reflection about the x-axis. Okay, so the height of the waves we refer to as the amplitude of the function, of the sine function or the cosine function. So the height of the wave or the length of the wave from in this case, because we haven't done any translations yet, no vertical translations, it's from the x-axis to the highest point on the wave, or the maximum point on the wave, and then which is the same as the distance from the x-axis to the lowest point on the wave. So we call a, the absolute value of a, the amplitude of the function. So next we're going to look at horizontally compressing and stretching the graph of sine. So again, I already have the values for the parent function filled in. Sine of 2x, so if we think about substituting each of these values of x and for x in sine of 2x, we'll get 0, and then we would end up having, when we substitute pi over 4 and 2 times pi over 4 is pi over 2, so sine of pi over 2 we know is 1, then we'll have 0, negative 1, 0. Notice that if we were to think about this graph, we would start at 0, 0, go up to 1, back to 0, down to negative 1, back to 0. So it goes through a full cycle. So that 2 is actually horizontally compressing the graph of sine. The graph is still oscillating between negative 1 and 1, so it hasn't done anything to the amplitude of the graph, but it has actually shortened the period of the graph. And we could finish filling this in, filling in our table. Okay, so then we have sine of 1/2 times x. So when we substitute 0 in, we're still going to get 0. But when we substitute pi over 4 in, pi over 4 times 1/2 is pi over 8. And you guys don't know what sine of pi over 8 is exactly. So we have to type that into our calculator, making sure that I'm in radian mode. I get approximately 0.38, okay, just to help guide my graph. When I substitute pi over 2 in, that actually turns into sine of pi over 4, which we know is root 2 over 2. And then we would have sine, when we substitute 3 pi over 4, and we'd end up with sine of 3 pi over 8. So again, I have to type that into my calculator because we cannot evaluate sine for 3 pi over 8. That's not an angle, that's on the unit circle. So we get 0.92. And then we'd end up with sine of pi over 2, which is, which is 1. And the graph will come back down. Okay, notice we only have positive values for sine here. So the graph is starts at 0, 0, and then goes up to its maximum value of 1, and then it goes back down to 0. But this is really only showing, our table values is only showing half a period of sine of 1/2 x. So x being multiplied by 1/2 or divided by 2 is actually horizontally stretching the graph. So the period of sine is also going to be horizontally stretched. And the period of sine of 1/2 x is actually going to be 4 pi. So it's doubled. So again, we can graph the sine quickly. I'll make it go between -1 and 1 again. Doing the best I can to do this quickly. Okay, so there's our parent function. Oh, we used orange. Okay, so now sine of 2x. So we still start at 0, 0, 0.38. Yeah, let's see, it's about there. Root 2 over 2. Oh, approximately 0.7. Uh-oh, what happened? I was missing some values. Sorry, we go up to 0.92 next. And then to 1, and then back to 0.92, 0.7, 0.38, and 0. So we can see a half of a period of sine of 2x. Or I'm sorry, sine of 1/2 x. Oh my goodness, I started graphing sine of 1/2 x. Ms. Dorset, fail. All right, let me go ahead and graph sine of 2x correctly. And do your best to not make the waves look pointy. Okay, so that's one period. Okay. And extending into the negatives. Sorry about that. If this wasn't already my second take and I had more time, I would redo this for graphing incorrectly first. But the orange graph is going to be y equals to sine of 2x, where we can see that the graph has been horizontally compressed. The period is going to be equal to pi. Okay, and then now we can graph sine of 1/2 x. Oops. Okay, so we can see we can't even fit a full period, or from 0 to 4 pi on our graph, but we can still extend the graph into the negative direction. We know that it's going to dip down below the x-axis now. Okay, so then in blue we have y equals to sine of 1/2 x. And the period of sine of 1/2 x is actually going to be 4 pi. And we can see that from negative 2 pi to 2 pi, which is length of an interval length of 4 pi, that we have all the negative values of sine and the positive values of sine. So the period for this guy is 4 pi. Okay, so in general, whatever the constant multiplying by the argument x is going to either horizontally stretch or compress the graph of sine or cosine. If b is greater than 1, it's going to horizontally compress the graph. If b is between 0 and 1, then it's going to horizontally stretch the graph. If b is negative, that's a reflection. So we don't want to deal with the horizontal reflections. And remember, by talking about sine and cosine being even and odd functions, that if we had, if we had something like y equals to sine of negative 2x, that because sine is a odd function, we could rewrite that as negative sine of 2x. Right, because the vertical reflection will look the same as the horizontal reflection. Or if we had y equals to cosine of negative 2x, because cosine is even, this can just be rewritten as cosine of 2x, because that horizontal reflection isn't going to make the graph any different. So since when there is a horizontal stretch, or a parent function has been horizontally stretched or compressed, it changes the period of the function. So the period can be determined by dividing 2 pi by b. And we saw that happen in the graph of sine of 2x and the graph of sine of 1/2 x, right? We said that the period for sine of 2x was equal to pi. So 2 pi divided by 2 would be pi. And the period of sine of 1/2 x was 4 pi, and 2 pi divided by 1/2 is 4 pi. So here's the steps we're going to follow for sketching sinusoidal functions. Okay, we're going to divide the period into 4 subintervals of equal lengths, because when we increment our x values using this whatever your period divided by 4 is, we end up hitting all of the x-intercepts, the maximum and the minimum values of the function. And then you can graph over one period and then extend the graph if necessary. So looking at this first example, we see that the amplitude would be 2, right? Looking at that 2 there. The period would be 2 pi divided by 3, since b is equal to 3. And we can make our table of values, where we're going to always start the table of values at 0. And to figure out what the next x value is, I'm going to take my period, 2 pi over 3, and divide it by 4, which is the same as multiplying by 1/4. Okay, so we get pi over 6, so I'm going to add pi over 6 and keep adding pi over 6 for filling in my table of values. So 2 pi over 6 is going to be pi over 3, 3 pi over 6 would be pi over 2, and then 4 pi over 6 is 2 pi over 3. Okay, and notice that this last value that you fill in on your table should always be the value of your period. Okay, so then you can fill in your table of values. Think about substituting 0 in, we get 0. We substitute pi over 6 in, and we'll get 2, 0, negative 2, 0. So I'm going to label the tick marks on this graph, since it's there's no domain specified for what we're graphing over. There will be on your homework, but I'm just going to have each of these tick marks follow what my table of values is. So scale by pi over 6. So super important how you label your graphs. Because otherwise it would be hard to tell that this is sine vertically stretched by 2 and horizontally compressed by a factor of 3. Okay, so you graph one period and then you can extend the graph however far you need to. Okay, let's do another example of graphing. So here we can see that the amplitude is actually going to be positive 3. That negative implies a vertical reflection or a reflection about the x-axis. The period is going to be 2 pi divided by 1/2, which is 4 pi. So making our table of values, four pi divided by 4 is pi. So we're going to have intervals that are length of pi. Okay, filling in our table of values. This is cosine. Cosine normally starts about 0, positive 1, but this is cosine vertically stretched by a factor of 3 and multiplied by negative 1, so vertically reflected. So the graph's actually going to start at negative 3, go to 0, positive 3, 0, back down to negative 3. And again, the domain isn't specified for what I need to graph over, so I'm just going to label my x-axis the same way that I labeled, or this with the same values that I used in my table of values. Okay, so we start 0, negative 3, pi, comma 0, 2 pi, comma 3, 3 pi, comma 0, and 4 pi, comma negative 3. And then we can extend our graph. Okay. All right, last example. So we want to write an equation that will fit this graph, and there's actually multiple equations that you could write to represent this graph. However, because we haven't talked about horizontal shifts yet, there's one equation that we could write. So we notice that this graph starts or passes through the origin. So we're going to use a sine function to write the equation. The period of this graph looks like it is pi. Okay, and the amplitude looks like it's a positive 6. And there's no vertical reflection because we know the parent function of sine usually goes up first, and this graph does as well. So amplitude is 6, period is equal to pi. We'll have y is equal to 6 times sine. We need b. And remember, we usually figure out the period by doing 2 pi divided by b. So we know the period in this case, and we can solve for b. Oops. So b will be equal to 2 So there is an equation that fits this graph. And if we thought about substituting, say, pi over 4 in for x, 2 times pi over 4 is pi over 2, sine of pi over 2 is 1, 1 times 6 is 6. So it checks. Next time, we are going to look at horizontally and vertically shifting the graphs of sine and cosine.